All right. I want to kick off a welcome to everyone. Say thank you very much for coming and attending this webinar. I'm really excited to have Nick here, uh, talking about the research he's done, working with agrology and all of his experience. And for background, I'm Adam Keppel. I'm the CEO and one of the founders of Agrology. I really love seeing some of the stuff out in the field that we've done and hear Nick's response to it because it's actually some of the stuff I got to design myself. I don't get to do a lot of engineering these days, and so when I do, it's fun. And I'm excited to learn what Nick has to share with us. Before we get started, I have a couple housekeeping things to say. First, please keep yourself on mute. Add questions into the chat and we'll pull them up at the end in an organized fashion. And then finally, please don't worry too much about notes or screen captures or anything. We will send out a recording, a deck, as well as a copy of Nick's conference poster presentation as a follow-up to everyone. So for as much as possible, please feel free to just sit back and relax during this and hopefully absorb the material as much as possible. And with that, I think my introduction responsibilities are over. I'm going to go ahead and turn things over to Nick.
All right. Thank you, Adam, and thank you for everyone for signing on today. I'm excited to share what I have with everyone. But first, I'm going to give a brief introduction about myself. I'm Nick Boogades. I'm currently a PhD student at Texas Tech University. I'm about halfway through my second year of my program. I'm originally from Edgewater, Maryland, which is a small town south of Annapolis. After I graduated high school, I started my bachelor's of soil and environmental science at the University of Tennessee. I was there from 2017 to 2021, and then I started a master's program at Texas A&M with Dr. Katie Lewis. And then I moved to Texas Tech, and I'm also a PhD student under Dr. Katie Lewis at the moment. My research in my master's focused on soil health, looking at soil health differences between organic and conventional peanut and cotton systems. And my PhD research is currently looking at carbon cycling and greenhouse gas emissions from regenerative cotton systems in the Texas High Plains. So I have a lot of experience with looking at greenhouse gas measurements, and today I'm just going to kind of share some information with you all about my experiences, things that are important when doing greenhouse gas measurements, and how to make sense of all the different systems that are out there and the options you have when you're looking to measure greenhouse gases, and the basic physics and things you need to think about when you're conducting those measurements. So if we think all the way back into history and think about soils and greenhouse gases and how we began thinking about this in the terms of agriculture, we need to go back and just think about how the greenhouse gas effect was discovered. So it started really early on in the 19th century with Joseph Fourier discovering that the Earth is warmer than it should be given its relation to the sun. And he discovered the greenhouse gas effect, where our atmosphere and the gases in it are able to absorb some of the heat from the Earth and keep the Earth warmer than it normally would be if it was just heat by the sun's temperature. Fast forward a little bit, and we get to Spotties Arrhenius's research, and he's really the one who discovered that humans do have an impact on the atmosphere and its temperature. And he wrote a paper called "On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground." And he really discovered that the gases that we're emitting through various human activities is contributing to the greenhouse gas effect, and it changing the temperature of the Earth. Come to the present day, in the 1950s, Dr. Charles Keeling did some research at the Scripps Institute of Oceanography at UC San Diego, looking at the variation in CO2 in the atmosphere throughout history and yearly variations. And that's this graph we see of CO2 emission throughout the year. That same Keeling curve. Fast forward in more modern day, in the 1970s, NOAA started monitoring CO2 atmospheric concentrations at the Mauna Loa Observatory in Hawaii. Going back way, way far into the past, we're able to see how much CO2 has been in the atmosphere throughout time, and we have ice core data that reveals CO2 concentrations back to about 800,000 years ago into the past. So that's going to be represented mostly by that top graph. We have Mauna Loa data since 1970, like I said, and you can see that there's that very steep increase in about the 1960s, and even earlier when the Industrial Revolution began, just showing that human activity is impacting the amount of CO2 in the atmosphere. And just for some reference, from 1980 to September of 2023, the atmospheric CO2 concentration increased from 340 parts per million to 416 parts per million. And 2023 marked the ninth consecutive year with a year-over-year increase of greater than 2 parts per million. So we are still impacting the Earth's atmosphere with our human activities, but many people through their research, such as what we're doing in our lab and around the world, are trying to address this challenge. And of course, the way we're addressing it, since we're a soil science lab, is how the role of agriculture plays into some of these effects. So if we look at kind of greenhouse gas budget of the US, we see that agriculture is not a huge factor. It's about 10%, but that is still a significant effect if you think about how much land we manage and how quickly we're able to change how we manage our land and how that can impact greenhouse gas emissions. It it reveals that we're able to significantly and fairly quickly change how we're impacting the climate through agriculture. So if we look at the gases of interest, of course, carbon dioxide is going to be the one that everybody talks about, and it'll mostly be the main focus of today, just because it's the easiest to talk about. But there's also methane emissions that occur from agriculture, and methane is about 25 times higher potency of a greenhouse gas than carbon dioxide. And nitrous oxide is also a really big greenhouse gas in terms of agriculture. About 70% of anthropogenic nitrous oxide emissions are from soil-related activities, and that is an even more um, harmful greenhouse gas, which is with about 300 times the global warming capacity of carbon dioxide. So we want to keep all this in the back of our head, thinking about how important some of this research that I'm sure many of the people on the call are doing. So with all that in perspective, we're going to get into what we really want to talk about, which is how do we measure fluxes of these gases from soil? How do we do it in an agricultural setting? And how can the way we design our system and think about the fluxes that we're measuring, how does it vary depending on the type of system that we're using? So primarily the gases that we just discussed are produced biogenically in the soil, either by roots or by microorganisms, and that results in a greater atmospheric composition or concentration of these gases in the soil than in the atmosphere. And that means we're going to see a diffusion dominated flux from the soil to the atmosphere as it flows from areas of higher concentration to lower concentration. So yes, it's going to be primarily caused by diffusion, but we'll talk about it a little bit later. There's some other things that can cause some mass flow events, which has to do with pressure changes or just disturbing the soil. But generally, diffusion is going to be the main driver of greenhouse gas loss from soil. And so this movement of gases or any kind of matter from one place to another, in our case, from the soil to the atmosphere, is going to be called a flux. So just a flux of one thing from one place going to another. And we can describe flux that's driven by diffusion from a very simple equation, which you see in the top right there. It's going to be flux is dominated by the gas diffusivity coefficient of our given gas, which can vary obviously based on what gas it is, but also on some of the nature of the chamber. But it's usually very specific to the specific chamber system we're using. And then that rate of diffusion is going to be dependent on the concentration gradient of the gas. So where it is in one place versus another. So it's going to be from the soil to the atmosphere. So fluxes are measuring or happening, but how do we actually measure them and what are we measuring? So any type of sensor or taking any type of measurement, you have to consider all the things that go into the number that either your instrument gives you or that you get when you do your final data processing. And so that's how we get to this equation, which is going to be how we get our measured flux. So this equation is showing that our measured flux is the sum of whatever the true flux is and all sources of bias, which come from errors that we make over the course of research as researchers, whether it's how we're using an instrument or how we analyze our data. And then there are sources of random error, which are typically just things that you can't control, just random variations in the technology that you're using or just natural variations in the environment. And we want to keep in mind that the true flux is always what we're after, so we want to minimize these other two effects. And we're going to talk about how to minimize mainly our source of bias today. But it's also important to keep in mind that, yes, we are adding these figures together, but our source of bias could cause our true flux to be lower than, or our measured flux to be lower than true flux, or it could be higher, either one. Getting into some of the different kind of chamber systems. So what is a chamber in the a soil flux chamber in the most basic sense? Well, it's really just a method of soil gas flux measurement where we contain a soil gas and uh, and interfaces directly with soil surface. And this is in opposition to something like an eddy covariant system where we're measuring concentrations and movement of gases above the crop canopy. If it's a soil chamber system, it's going to interface directly with the soil in some way. We need to concentrate the gases or at least contain them in some way so that we can measure them. And then we want to make sure that we have flow through the system at some point so that we can have flux being transferred into whatever our containment device is. And so we can do that in multiple different ways. We can have an open system or a closed system. In an open system, gases continually flow in and out of the system throughout the measurement period. So gases aren't replaced into the system like they would in a closed system. They're either flowing out at a consistent rate through, you could use a pump to force the air through, or you could have a diffusion-driven process where your diffusion rate out of the chamber is dependent on what the actual concentration is inside the chamber, and then you can do your flux calculations from there. In closed chamber systems, there is a buildup of gases, or the gases remain within the system throughout the duration of the measurement, and you're measuring the increase in that in the concentration of gases in the system in order to get a flux rate. And then when we talk about automated versus manual systems, there's kind of varying definitions. So when I presented some of this research at a conference, I said the picture on the left, which is the system that I have been using for a long time, that's my manual system, and the agrology system is going to be the automated system. But they're like, no, I would consider your system automated system. We method was in that diagram below, and then the true manual system. Well, if you're just comparing between the two systems we're going to talk about today, one is obviously manual and the one is automated. So when we talk about our closed system with the lower, that's going to be our manual system, and the agrology system is going to be considered our automated system because it's continuously and there's nothing to.
Nick, I'm sorry to interrupt here. We've noticed for a couple minutes here we're having audio clipping issues. I'm not sure
Okay.
why, and they look like they fixed themselves. They unfixed themselves, but we're not hearing all the great stuff you have to say. Is there any adjustment you can make on your end, you think?
I can try. Sorry, I just saw text. Let me see what I can do.
I certainly know it's hard when you're presenting to get that kind of feedback.
Yeah, sorry.
Yeah, of course. First, I thought it was just me, and then we found out it's not.
Let's see.
Thanks everybody for the pause here while we try and diagnose this issue. If you have a question in your mind, now's an excellent time to go ahead and throw it in the chat so we can queue them up.
Is this any better?
It sounds better. Let's roll with it and see.
Okay, just give me a heads up if not, and if it does, let me know, and I could try to just go to my computer audio.
Okay.
Okay, and do you know when it started? I could go back and
I think it
try
got
to.
really bad a second ago when you're talking about the difference between automated and manual here.
Okay, well, so basically all I want to say is that this picture on the left that you see with the gas met and the Lycor, that can be considered a manual system. The agrology system are going to be considered automated. I know there's varying definitions, so I just want to look that up. Are we doing better on the audio?
Sounds good to me, folks. If you're still having trouble, just please pop it in the chat and I'll track it.
Okay, yeah, I did see the question, the chat room. Okay, all right, on to the next slide. Okay, so going into closed chambers a little bit more, I might skip over this just a little bit more because I kind of went over it already. Hopefully everybody saw it. But for closed chambers, we're just measuring an increase of gases in that space of the chamber over time to calculate that flux rate, and air is not replaced. So we're measuring for 10 minutes. We're going to be building up gas in that headspace of that chamber that flows out of the soil into the chamber over the whole course of the measurement. And when that occurs, we get an increase of gas concentration over time. So if you look at the graph on the bottom, our CO2 parts per million is going to be increasing over the course of this about 8-minute measurement that we're looking at. So about every 20 seconds, this system is giving an increase in CO2 concentration, and then we can measure the slope of that line, and that when we can directly relate that to the flux rate of any gas that we see that is measured by the system. So it could be CO2, methane, or nitrous oxide. And then we have to do some clever math to get from parts per million to an actual weight of gas, which is how this data is typically presented. So when we first get our data, it's in a concentration, and that concentration is going to be in liters of gas, since we're dealing with the volume of the chamber. And then we can use the ideal gas law, which is a pretty simple equation to go from our volume of gas of interest in the system to our moles of gas, which is going to be that red N in there, and that's what we're actually solving for. And so it gives us an output in typically the first measurement we get is in micrograms of carbon dioxide per meter squared per second, but we can scale it up to a more usable unit like kilograms per hectare per day, tons per acre per day, and so on. So continuous open chambers work a little bit differently. They're the same basic measurement principle. However, the chamber is more permanent, and it continuously monitors those gases. And for systems like we're going to talk about today, they don't have a pump in them. They're just have a ventilation system that's engineered to have a specific diffusion rate of a gas out of the system depending on the concentration within the system. And so we've talked about how the chambers work, but there are some challenges when it comes to measuring with chambers. Chambers are great. They're an awesome way to measure soil flux. Unfortunately, using them affects the way that soil or that gases leave the soil. It's going to affect our flux a little bit, but there are to mitigate with some management practices.
Nick, unfortunately, we have audio problems again. I'm sorry.
Okay. Me try using my computer audio. See if that helps a little bit.
Thank you. I wanted to nip it in the bud this time.
Yeah, let's see. Um,
Nick, unfortunately, we can't hear you, but the picture's back. So halfway there.
Can you hear me with this setting?
Yes.
Okay, I'll go with that. And all right, just let me know if it happens again. I tried a different audio source.
Okay. That sounds pretty clear.
Okay, sounds good. All right, so getting back to our challenges with the chamber system, they're great, but the way we use them can sometimes affect the way soil gas fluxes happen. But we're going to talk about some best management practices to try to mitigate those challenges. And some of the different systems are going to have different challenges. Compound this with trying to do all these measurements within an agricultural system, and it brings another set of challenges. So our management activities that impact greenhouse gas emissions can make it difficult to measure or affect the ability of some of these systems to measure within whatever our target system is. So some of the specific challenges to chambers are going to be that diffusion rates slow as chamber concentrations increase. So if we talk about that closed chamber system, we're building up the concentration, and really with any chamber system, measuring the concentration of gases that would normally occupy that area. And so that is going to slow down the diffusion rate as the concentration of that gas increases. So in an ideal world, a perfect flux calculation would accurately predict the flux rate of whatever system we're trying to measure just prior to the chamber being closed if you're repeatedly opening and closing the chamber. However, we don't really have a way to do that. It's kind of physically impossible, but that's always what we're striving for, is to be able to accurately predict flux without the influence of the chamber. Another important thing is that pressure fluctuations from wind and other conditions need to be transferred onto the soil surface because those are going to be affecting fluxes. And if it's happening to the soil around your chamber, you want it to happen to the soil in the chamber. So most chamber systems are vented in a way to communicate pressure differential or pressure changes from the outside to the inside of the chamber. Another consideration is that when we install chambers, we're going to be disturbing the soil, which can cause some of those mass flux events that we're talking about. So if you're breaking up soil as you're installing a chamber, that can temporarily increase the amount of flux from the soil simply because of the disturbance. So typically we want to wait a lot of times it's 6 to 24 hours before events, but 24 hours is usually a pretty good standard to go with. Chambers impact soil within or under them. If you have a chamber that continuously covers the soil, you can't have plants growing in them. So if that's something you're interested in looking at with your research, you're probably going to be unable to do that. But another thing is if you have a collar which interfaces with the chamber, as you see picture here, that's going to be affected by different things compared to the soil around it. So there might be some shading on the edge of the collar, which causes the soil inside the collar to be a little bit cooler than the soil surrounding it, and so on and so forth. And there's also the challenge with manual systems of what time of the day do you want to measure, and that's really just going to come down to researcher preferences. And just want to check, are we still doing good on the audio?
Much improved. Thank you.
Awesome. Okay. So getting into some of the challenges specific to agriculture is that chambers need to be removed for some management events. So that can limit the. Fortunately, some of those management events that we need to remove chambers for impact fluxes. So those can be irrigation events and so
And
on.
Nick, you're going to hate me, but a second I said it was improved, it got unimproved naturally. Uh,
Okay.
I mean, the only other suggestion I've seen, which I've heard, is there any chance your uplink is low bandwidth? I'm guessing no if you're on a university one, but we're running out of ideas here. Uh,
Probably not.
the thought is sometimes I know Zoom can struggle with having the camera on. Um,
Okay. I could try turning mine off maybe, or
yeah, let's try that. I
okay.
hate to ask that since you're presenting, but I'm also out of
All good.
ideas.
Okay, here we go. All right, just give me a heads up if it starts cutting out again. Okay. So talking about those challenges specific to agriculture again, um, there's a challenge of how to accurately represent our managed events without impacting fluxes. So those management events can be irrigation, fertilization, and tillage, when a lot of times we can't be in the field taking those measurements with when those management events or soon after those management events occur. So all of that is what we're going to be thinking about today in the case of my research, since that's kind of what this project is based around, mainly just the research site. But I thought it'd be good to give a background on what we're looking at through my PhD research and how the work we're doing with agrology kind of fits into there. So my PhD, as I said, is looking at carbon dynamics and greenhouse gases and regenerative cotton in the Texas High Plains. So what we're trying to investigate in the High Plains is that we're a very important region for cotton production, producing about a quarter of U.S. cotton bales every year. But we're a semi-arid climate with low precipitation and a low adoption rate of conservation practices, which makes us really susceptible to future environmental challenges. So we want to see how regenerative agriculture can be used to benefit long-term sustainable production in the region. So our lab's definition that we use for regenerative agriculture is the continued capacity of agricultural systems to function in a changing climate that supports soil, communities, economic output, environmental sustainability, and resilience to the outside threats of these outcomes. And some of the practices that we've identified in the region that can achieve these goals and therefore be considered regenerative are going to be cover crops, crop rotation, and reduced tillage. And these encompass the two systems that we're going to be looking at with the help of agrology on really trying to nail down, in this case, how regenerative agriculture impacts greenhouse gas emissions. So this is a quick overview of cotton production in West Texas. Our conventional cotton systems are relatively low input, low intensity, and include this long fallow period from about November to May, which can impact the amount of carbon we're sequestering in the soil, and it'll also have an effect on greenhouse gases. So the two regenerative systems that we want to look at is a no-till cover crop system, which is in the middle there, and it's basically the same as the conventional system, but we're eliminating tillage and inputting a rye cover crop that we plant right after cotton harvest, and we let grow from November to late March. So we want to see the impact of this cover crop system um, on not only carbon but greenhouse gases. And then if we look at the other regenerative system, which is going to be a cotton wheat rotation, we have the same cotton production timeline, but we plant wheat directly after cotton harvest. And then we have a long wheat growing season that goes until the following June. And then we have an extended fallow period from June of, let's say, 2025 to May of 2026. So a long fallow period, and we want to investigate how that impacts carbon cycling and greenhouse gases as well. So if you look at the data that I currently get, just a quick overview of what it looks like when I have my greenhouse gas data. I'm measuring on approximately a 3-week to 1-month basis. So I get data that looks like this throughout. So we're playing in harvesting in October, November area. And so I end up with about 8 to 10 measurements throughout the course of the growing season. And we see these general trends that when plants are growing in the field, we see increases in carbon dioxide emissions. But there's a lot of stuff that goes on in between when I'm measuring, if I'm only measuring on a 3-week basis. And so we wanted to compare how the way I measure currently with the manual closed system every 3 weeks compares to continuous data from an automated system, which is going to be the agrology sensors. And so that was kind of how the idea for this poster came up, to compare manual and automated systems from from our soil gas flux measurements. So the manual chamber systems are kind of the standard that everyone uses, but there's a lot of criticism because of the short deployment time and long measurement intervals, bring into question the representativeness of that single measurement point for the period it represents, which is going to be about a 3-week time. I've gotten lots of questions about this, and most of my presentations research I just went over. So this poster also served as a way for me to validate the methods that I'm using and just compare what kind of data we can see from an automated system, and seeing if those once per month sampling intervals from a manual system, how do they compare, and are they representative compared to a continuous automated system? So the objective is to determine that representativeness, like I just said, and the impact is going to be that if we have longer measurement intervals from a manual system, it can save time and money compared to shorter intervals. But those automated systems could provide greater resolution and are a little bit less labor intensive. So there's benefits on both sides. Just to go in again, this is an overhead picture of the research that we're going to be looking at. So we're only going to be focusing on the cotton wheat fallow and the no-till cover crop system. And we're going to be looking at 3 replications in each system of a paired agrology chamber with a soil collar for gas mat measurements, which is going to be the other instrument that we're using. So more detailed picture of both of the systems. The gas met is going to be the GT 5000 Terra with a Lycor 800S smart chamber. It's that closed loop system that's manually operated, and we get a little under 100 data points for daily flux calculations between the replications. We're taking 8-minute measurements per plot with 3 weeks, about 3 weeks in between the measurement events. And then the continuous system is going to be an automated static system and it's a continuous chamber flow through, and we're getting about 9,000 data points for the same representative time period. There's automatic flux calculations, and the chambers stay in place all season. And if we look down below, what we're going to be looking at is going to be a series of 4 sampling events that are about 3 weeks apart when we go into looking at the data. So as I said, a direct comparison between these two systems. Again, we're looking at an overhead picture. If you look at that green system that's in the most foreground of the wedges of the pivot, that's going to be the cover crop system, and directly to the right, that other wedge is going to be the rotational system. We're going to be doing statistical comparisons between the two chamber systems within a production system within a management event, just to confirm that the fluxes that we're getting between the two systems are the same and they're not different, because we want to make sure that they're measuring the same thing. But what we're really worried about is how those two systems represent the flux dynamics of the two production systems differently. So how do the average daily flux measurements of the agrology system over 3 weeks compared to the single data point of the manual system? So just a snapshot of how the manual system represents different fluxes. So if we look on the bottom right, if I take a measurement on 8/28 of 2024, a week and a half before that measurement is going to be representative of part of that 3 weeks, and then the back half of that week and a half segment is going to be the other half that it represents. The week and a half before 8/28 is going to be averaged with the other measurement 3 weeks before, and then the other side is going to be averaged with the measurement 3 weeks after. I might be able to explain that a little bit better later on, so I'm just gonna wait there. And this is just, again, showing the manual system that we're using. So it's a closed loop, gas enter the chamber, they're fed into the gas met, read every 20 seconds, and then they're returned to the chamber so that the increase over time can be measured as a slope, like we said earlier. And then I'll go ahead and let Adam explain how the agrology system works a little bit better, since he is the expert.
Absolutely. Thank you, Nick. So, audio seems to be going great first off, which is good. Thanks for fixing that. Sorry for the trouble. What I'd emphasize here is, we set out to design this chamber. We want to make something that was autonomous, scalable, and affordable so it could get more real data from more real land. That was really the driving goal here. We, of course, being the lazy engineers that we are, found the USDA ARS GraceNet design protocols and thought, hey, let's follow this. They've done a lot of the work. I'm joking. We just wanted to conform to it because it was a great guideline for how to take quality measurements. I really appreciate that document being available. We tried to combine the benefits of automated and manual chambers as much as possible and avoid downsides. To simplify this device, it measures the gas concentration in the chamber directly. It doesn't have a pumping circuit or anything like that, as gas is diffused through the chamber and through the venting system. Because it's enclosed all the time, it can capture rapidly transient features that are interesting that traditional approaches can miss, both manual sampling and chambers that open and close. The venting system is something we designed that's outlined in a white paper we did that characterizes diffusion across the venting at different concentrations to account for the release of gas out of the chamber as well as gas entering the chamber. And the key things I'll emphasize here is it's relatively small, so that the soil outside the chamber is influencing what's inside the chamber. Same reason as a built-in shallow chamber collar, so that the soil outside the chamber can be influential. Those sensors are inside for direct measurement. We've eliminated all the moving parts because those don't work well in an agriculture environment. And overall, it's just a affordable, durable system that has been working well everywhere from at this point we've deployed in Puerto Rico all the way up to pretty cold regions of Canada. So that finishes my quick explanation here. Nick, I'll pass it back over to you.
All right, thank you, Adam. So keeping all that in mind, let's see. So keeping all that in mind, let's get into the data. So this is the data comparing the two measurement systems to validate that they are measuring roughly the same thing. So here we're looking at the different systems are different colors. The cover crop system is represented by the green bars, and the rotational system is represented by the maroon bars. And then the different systems are broken up by the shading of the bar. So agrology is solid and the gas met, which is the manual system, is outlined. And we're looking at our CO2 flux rates in kilograms of CO2 per hectare per day. And the way we break it up, making comparisons within date and within production system, that gives us a total of 8 comparisons for this study period that we looked at, specifically from August 7 to the 10th of October. And so what we see is, comparing through those 8 different systems, um, those calculated fluxes only significantly differed between the measurement systems, the agrology or the automated and the manual systems. They only differed at one event, which is in the cover crop system in that October date, and that significance level there was a value of zero point 0.9 significance level. So for the part, these systems are measuring the same thing, which is good. That means that they should have a same general trend. And you can see that those bars do have the same general trend. So we got that out of the way, and then we got to look at what we're really interested in is how do these two systems compare in what they're measuring and how they're measuring changes in these gas fluxes over time, and how does the measurement interval going from every 3 weeks to continuously getting 10-minute data, how does that change what our fluxes look like? So these graphs are a little bit confusing, but I'll try to explain them the best I can. So if we go back to that overhead picture of the pivot that we're doing this research in, there were those 2 wedges, and each of them had those 3 white circles in them, and represented 3 replications of each system. This is going to be looking at a snapshot of one measurement event with the manual system. So 1 3-week interval in one of those wedges. And each of these graphs is representing a specific pair of the manual systems and the automated systems. So what we're looking at on the specific graphs again is CO2 flux rate on the y-axis, and then on the x-axis we're looking at our different dates. These manual measurements took place on August 28th. So we're going to be looking at a week and a half before and a week and a half after that measurement, which is what's shown on the graph. And so the blue dashed line is going to represent what that one daily rate we measure the manual system represent for that whole 3-week period. So going from let's see, we took that measurement on the 28th, and it was right around 50 kilograms of CO2 per hectare. But what we look at on the gray agrology daily average graph is the exact daily average from each one of those days across that 3-week period and how it changed over the 3-week period. And then the maroon line is the average of all of those green dots, and or those gray dots, sorry. And what we see is those lines are actually really, really close together, especially if we think about the scale and the magnitude of the flux differences we're looking at. And almost all of the replications were going from right around 50 kilograms of CO2 per day at the lowest point and all the way up to 200. But we're seeing that the difference between the two systems is only around 20 to 25 kilograms of CO2 per hectare per day. So they are measuring very closely, and that 1 3-week period, or that one measurement for 3 weeks, is a pretty good measurement of what we're trying to get to the bottom of. However, I will say that part of what we're seeing is an effect of where we're doing research. So I mentioned that some of these challenges are specific to agriculture. Well, this research is being done under center pivot irrigation. So with the gas met system, we can't measure very close after an irrigation event because it doesn't handle moisture very well, and you just don't want to be walking through the field when it's as wet as it is after irrigation. So you'll notice right before the measurements occur, which is what those green bar or those blue arrows are representing, the manual system is slightly overestimating the flux rate. But then after the irrigation event occurs, which happens about every week and a half at this location, you see an increase in that agrology and the flux measured from the agrology chambers. Well, that's just fluxes that we can't capture because it's too wet. So that kind of evens out the fluxes. So some of this is a specific effect of where we're doing our measurements. So if we go back to this graph that I mentioned before, the main effect that we're seeing here is the presence of is the presence of plants in the field affecting microbial respiration. So when there's more carbon being exuded by plant roots and released from above ground biomass, that's what's really driving it. But we know, based off of the graphs we just looked at, that irrigation is also impacting these spikes and troughs of fluxes within kind of a 3-week period. So if we look at just the hydrology data from the entire season, which is what this line graph is going to be representing, we see that these irrigation events, which are represented by the blue arrows this time, are causing a pretty interesting effect for CO2 emissions. So again, we're looking at kilograms of CO2 per hectare per day. Same colors for the system's rotation in maroon, and the cover crop system is in green. And again, those blue arrows um, are representing the irrigation events. And you'll notice that the spikes for the irrigation events are just barely offset for each system. And that's because the pivot takes about a day to go from one system to the other, and it goes through the cover crop, or sorry, not the cover crop, the rotational system first. So the maroon graph. And then it takes about 24 to 26 hours to get to the cover crop system. So we're seeing just barely offset those peaks happen in the rotational system just before they happen in the cover crop system. Now, we probably could have guessed that this was happening, but with the manual system that we have, there's not really a way to confirm it, because it's you just can't use the manual system when it's as wet as it is after the irrigation events. So it's really interesting to see the data from the continuous system of what is the magnitude of these increases days or even hours or minutes after the irrigation comes through, and then the time delay effect between it happening in the conventional system and then the rotational system. So those arrows are from the first of the graph when irrigation is happening, but we have the same thing when rainfall occurs. If we get a rainfall, we can't measure. Um, okay, sorry, I see that we have a question that is
Nick, I was
really
about to
currently
pop in with that.
Yeah. Let's see, Tom. Footprints around your device are probably influence of gas flux of the soil. So that is a great question. So I'll go back. Let's see. So yes, so there are footprints from around when this device was installed. Um, Unfortunately, it's not really possible. And again, this is more of Adam's expertise, but it's really difficult to install without being directly over where we're installing. We try to be on the other side of the row when these chambers are getting installed. But I will say, specific to this research site, it is a very, very, very sandy soil. So about 80% sand. So the impact of foot traffic is a lot less than you'd see from like a clay or any other fine soil. So yes, those can be influencing fluxes, but overall, I think the impact in compared to another kind of system would be a little bit less. But that is, of course, something to keep in mind. But the same thing happens with my manual systems. It's really hard to not be right over top of them sometimes, especially since I have to measure the height of each collar. So that's a great question. And again, that's just one of the things that kind of goes with um, the nature of measuring like this, and it's something that researchers should be very, very aware of.
Yeah, I'll also highlight real quick, Nick. It's not just this type of measurement. Everything we measure ever affects the measurement. That's just the nature of measurement. Better scientists than I have said that in better terms.
Yeah, very, very difficult. So going back to this graph of our season long data, irrigation is going to be the most consistent form of soil moisture that we get during the season. This year we had a wet September, so that's what this blue bar is highlighting is a bunch of fall events we got all throughout September, causing different fluctuations in the different systems. Um, and again, you see that same kind of peak and trough trend that we see in the irrigation system, but with the manual system, again, we wouldn't really be able to measure those quite as well because you can see how rapidly those peaks and troughs happen. But with the manual system, if it's too wet, we just can't get out there to do it. So I think, let's see, we got about 15 minutes left. I wanted to leave plenty of time for questions, so I'll go through conclusions really quickly, and then hopefully I have plenty of time to answer questions, and hopefully um, not too many of them will be related to not being able to hear me. So really quickly, manual and automated systems come with different considerations for implementation. but a lot of them can be shared. So like Tom brought up, um, carefully trafficking around your flux measurement device is going to be important, considering when you need to make certain changes to make sure you're accurately representing what you're trying to measure is going to be very important, but it is going to differ between manual and automated systems. For example, in manual systems, you may be trying to control whether there's plants within or not within your chamber. But in an automated system, you're not really going to have a choice. Plants just aren't really going to grow under a continuous automated system that just stays in place. So in some situations, depending on your study design, these systems will yield similar results. So for my research, I don't include plants into my collars when I'm measuring with my manual system. So plant presence under the collar isn't a huge consideration for me. It's also important to understand the general rules and best practices regarding chamber-based measurement theory, as these are the guiding principles for study design and chamber deployment. So there are some overarching themes when it comes to soil gas flux measurement that we want to keep in mind and try to use those best management practices as much as we can. And as I stated before, we want to remember that the flux we're measuring is some combination of the true flux, our errors, and our random variance. And the smaller we can make those biases that are researcher induced, the closer we're going to get to the true flux. And that's really the most important thing to keep in mind. And for that, I want to thank everyone for attending. I'm very sorry that I didn't realize um, the audio issues immediately, but I think we have enough time if we have to go back. Um, So Dr. Michael, yeah. So we're talking about flux towers in a second, possibly. So we can get to that, but hopefully, um, if we have time to about things that you couldn't hear me great with, we can do that. But thank you all for attending, and I want to say thank you so much to Dr. Lewis, my PI, leader of our lab. She's a fantastic researcher and has is really just the reason why any of the success happens in her lab and with her students. So thank you a bunch to her. I think she's on with us. And if anybody wants to get in touch with me, there's my email, my LinkedIn, and if you want to see the research that Dr. Lewis's lab does, there's the link to it. And I just want to acknowledge my funding source for my PhD research, which is the Sustainable Ag Systems Program of USDA. So thank you a lot for them. And with that, I'll go ahead and open it up to questions. And I'll
Yeah.
open up the chat as well.
And Nick, before that, I just want to say no worries about the audio issues. Thanks for tolerating those interruptions while you worked through them. I really appreciate it, as does everyone else. And thank you for taking the time to walk through your research and the mechanics of soil chambers today. I really enjoyed it. It's fascinating to hear about the work you're doing and not just how these things work high level, but how you're applying them to your research, which was super fun. We have a range of questions here. And unfortunately, on the subject of gas flux, my daughter's preschool has a gas leak today, and
Oh,
I have to go take care of her in a few minutes. I lead a gas focused life, I guess. And so I'm going to be turning over MC duties to Holly Nuss in a couple seconds here to help you work through these questions. But we have quite a few, which I'm excited to see, and I'm excited to hear answers to them.
awesome. So let's see. Well, I'll address Michael's question first because I think that was the first one that I saw get brought up, at least where I'm scrolling. And so we talked about seeing negative fluxes. So yes, if we do have plants in the chamber, it is very likely that we would see negative fluxes since photosynthesis is going to be drawing in CO2. And that's one of the things actually meant to bring up earlier is that I said closed chamber systems measure the buildup in gas concentration over time. But what we actually see a lot of times with nitrous oxide and methane is that there is a drawdown. So we do see negative fluxes from other gases. For carbon dioxide, I exclude plants from the chambers because sometimes plants get so big that they can't fit in the chamber anymore, and that really complicates trying to measure fluxes. Or if you happen to nick a leaf, that can actually dramatically increase CO2 flux. So I try to keep them out. So I'm only measuring soil flux, not net ecosystem exchange. And we try to incorporate some of the other effects of a cover crop or photosynthesis by measuring above and below ground biomass, and then soil carbon. So to try to get that net system exchange. And Holly had mentioned possibly being able to unmute people, but I'm not sure how to do that. Let's see.
If not, Nick, we can use the chat. I know
Okay.
Dr. Michael said he could weigh in on Flux and EC towers. Thank you, Dr. Michael, for offering that. There was also another question about the time of day of sampling, and maybe you could
Yeah.
address that, Nick.
That also a great question. So obviously for the continuous systems, that's not a problem. And so that's another consideration that we need to have for the manual systems. So the way we do it is we try to measure when fluxes have more or less stop changing. So that means in the middle of the day. And the reason we wanted that is because we don't want to go measure one system in the morning when the flux rate is still increasing or still changing, and then go to another system where it's the middle of the day, fluxes are at their highest and have stopped changing. And then really all we're measuring is the effect of when you measure one system versus another. So we typically try to measure in the early afternoon to the late afternoon because that's when fluxes are going to be the most stable. So that's going to be anywhere from usually 11 a.m. to about 4 p.m. is when we try to measure with the manual system. And so in thinking in that, that's just even another to look at the comparison between a manual and an automated system because you want to see you can try to limit the effects of measurement time as much as you can, but there's human factors. I can't be out there all day measuring, and I'm kind of measuring when fluxes are at their peak. So you would think it would be overestimation. We do see that as an overestimation, but then the irrigation kind of evens it out. And I see that Michael looks like he got to unmute himself, so I'll let him go if he has anything to add.
Yeah, I would probably make a couple of comments from my perspective, and just for the people that don't know me on the call, I run 6 sites that have Flux towers, and we've been running the agrology systems on 2 of those sites. And so there was a question regarding Flux towers. What we're finding, and we haven't really fully published that, but it is not unconceivable that you couldn't deduce that from biology or agriculture or plant sciences 101, is that actually there is quite a degree of variation from a spatial as well as temporal perspective, with respect to from a crop to crop perspective, from a location to location perspective, from a year over year perspective. So the flux tower problem becomes one of cost. A fully embedded system, if you're really measuring all the gases you would want to measure, you're looking at about $250,000. If you now come to the point that you start realizing that this is not a one measurement, one season, or one crop and done type of an approach, but you actually have to do that continuously. You probably would have to do some experimental design on the whole thing and yada, yada, yada. You come to the point that all of a sudden the whole cost is really exploding, because the ingoing assumption that one soil will behave this year this way and next year it will be behaving exactly the same way and the third year it will be behaving the same way is just simply not correct. And also when you move that one from that field, you move it to the field that is just a mile down the road, or you move it to a field that is in a different state, your data is changing. And we just simply do not have yet the correct algorithms to actually unpack that as to why that is really the case. I think we have a very, very infantile understanding of how that actually is operating. And that is where the crux of the flux towers comes back, that they are expensive while accurate, and they are integrating over the entire field. They're just not doing, they're just expensive, and we'd have to do a lot. And then I wanted to weigh into one point about time of day sampling. That is the high level true that you could measure at one point that you want to pick, but you really need to be careful about understanding when exactly is actually or what defines that point of time. People will have the conventional assumption that at noon that's the highest temperature, so that's the highest amount of activity. That's actually not correct, and it certainly is not correct the more northern you actually go. Because what we're seeing, for instance, is that the lowest temperature in soil, and that should be paired with measurement of whatever gas you measure, is actually the lowest temperature is somewhere between 8 and 10 o'clock in the morning. So by noon, the temperature is not yet maximum. The temperature is maximum at about 3 o'clock or 4 o'clock. So what is happening in research is frequently that people go out in the morning, they're like, oh, well, that's probably on a synodal curve. It's kind of like the average, and therefore I'm getting my measurement as an average and I can extrapolate. That actually needs to be verified and validated before that is when you measure. And that is where all day measurements are coming in handy because you start actually seeing how the curve of temperature and fluxes is changing over the day, and you'll be surprised on how they are actually changing. And there are various patterns that actually go in there. So that's something that I just wanted to address on the time of day side. And flux is differing within a sample area. I had addressed that one. I think we're in the nascent stages of understanding what the variance is across the field. And I would probably guess that a 20 to 30% flux difference as an ingoing assumption across a field of, say, 40 hectares, 80 acres is probably it might be on the high side, but 10 to 20% is probably what I would say, which is kind of like a generic standard deviation that you should apply for anything that biology is.
Yeah, so those are all great points, and time of day, of course. I'm trying to mostly maximize like a flat curve. Understand that there can be a big flush in the morning, and it's very difficult to measure. And one of the things I do want to explore in the future is using these manual systems more times during the day. It's just a little difficult. Research site's an hour away, and it takes about 6 hours to do all the measurements. So it is tough to get them around, but. I did want to quickly address some of the other questions I see in here. So let's see where to start. Okay. Um, let's see. Chamber installation, mass flux is happening. Is it increase in microbial activity? Possibly, but there could also be physical pore space that is limiting the amount of flux coming out of the soil, and that's going to depend soil to soil. And then time of day, we addressed that. Footprints, address that a little bit. I think I kind of addressed too what happened on 9/6 to spike the emissions. Lots of rainfall in September, so that's what all those spikes were. Negative fluxes, I think we addressed that. Let's see. Cover crop system. Here's the one I wanted to see. Okay, cover crop system seems to be emitting a lot more. Yes, we are seeing that. Is that the cover crop system is our highest emitter. It's going to be significantly more. This is just based off my manual data, but significantly more CO2 flux throughout the year from the cover crop system, and then the rotation is not significantly different from the conventional system. Those are significantly lower than the cover crop system. However, we are seeing from a soil organic carbon perspective a significant increase in soil organic carbon in the upper depths of soil in both of the regenerative systems. And then we're taking
Maybe
go
maybe
go
let me
for it.
chime in into the cover crops there. One of the things that we observed in one site, and that may be the answer as to why you're actually seeing higher emissions there, um, is that we've had one field which is an organically managed field, and they are doing rice. And what they do is they grow a cover crop, and then what they do is they roll that thing and they seed into that, and then they flood the field. Now, what you have happening there is you actually have in a anaerobic environment because you flooded the field, you have a decomposition of the organic matter. And that is a characteristic of your cover crop. So yes, you're going to all of a sudden be seeing very high spikes of a number of things. And If you're seeing a high spike of CO2 emissions happening, you might want to look at what emissions of methane are you actually getting at the same time? Because what you're likely doing is likely doing a decomposition of organic matter, which is why at certain times we're going to see increases of the CO2 emissions.
Yeah, that's definitely what's happening. And the reason we think that there's a difference between the cover crop and the rotational system is the cover crop is going to be a relatively young rye plant when it's terminated and added to the soil for decomposition. It's going to have a lower C to N ratio, more quickly utilized by microorganisms, and increase overall CO2 emissions. But then when looking at the wheat system, if you go back and look and think about that, um, the yellow color in this graph. This is actually also the rotation, the yellow color there, but that's in the wheat fallow phase. So we have that the rotational system replicated twice. One is planted to cotton every year, and one is wheat fallow. So early in the planting season for cotton, we have wheat that's still growing. So that's why you see that it has the significantly highest amount of CO2 emissions. But then once that rye is terminated or harvested, more accurately, it's more of a recalcitrant form of carbon, higher C to N ratio, more or higher lignin to cellulose ratio, and so it's more difficult to quickly decompose, and so that's why you see it a little bit lower throughout the rest of the year. And then I don't know if Holly, I know it's a little bit past time. Do we still have time to keep going, or do we need to kind of shut it down?
Yes, no,
Either
we can
one's
keep
okay with
going. I
me.
mean, I'll say
Okay.
thank you to everyone for attending. If you need to jump, go ahead and jump and we'll send the
Yeah.
recording out. But if you want to stay on
Yeah.
and continue the discussion, we can continue answering questions.
Yeah. And great. There's great input here. I'm trying to catch up on anything else I see in the chat.
Just responding to Tom
Automated.
Wiley, who asked about flux towers also measure methane and nitrous oxide. Yes, if you buy the sensors for that one, then they will also measure the methane and nitrous oxide. The methane sensors and nitrous oxide sensors are somewhere between 60 to 80,000. And you have to integrate that. There are a couple of challenges with respect to measuring really low concentration components. We also are aware of a ammonia sensor that is a flux sensor, open pass sensor that is made by a company in China called Happy Photon, which might be actually a good and interesting sensor if you're actually looking at the entire nitrogen cycling aspect. But again, to reiterate, a flux tower is integrating over the entire field above the canopy. For a flux tower to function, you need to be about, for atmospheric and boundary layer conditions, you need to be above about 2 meters, 6 feet above the canopy. That means you are integrating also over what is the plant doing in the whole thing. And then you have to go back and basically back out what the plant contribution is by various assumptions. If you're taking a soil chamber, such as in the case of the manual chamber that was presented, or the agrology sensor, then you're limiting yourself to measuring what is going on from the soil. Soil is predominantly doing the methane and the nitrous oxide action. So you should be seeing a alignment between methane and nitrous oxide values you're measuring from a soil chamber with what you're measuring with a flux tower. Not so for CO2, because then the whole photosynthesis comes in.
Yeah. So agree with all that. Let's see. Oh, sorry, I got a message that one more question came in, but just also to address that, as Michael said, yeah, a lot of that, the methane and nitrous oxide are coming from the soil. So if you're just using a soil-based system, it's really easy to see those, and a lot of times you'll see negative. At least in our systems, we see both negative and positive nitrous oxide emissions and negative methane emissions. So it's really easy to tease those out with a soil-based emission, soil-based flux system. And then what was the other thing I was going to address? Can't remember it off the top of my head, but I see another question here from Stephanie. Did the agrology sensor stay in place for the full 3 weeks of the comparison trial? How might that have influenced the result? I understand soil stays covered by the agrology sensor. Wouldn't that have an influence on soil conditions under the chamber compared to conditions in the manual chambers? So, for the first part of that question, yes, the agrology sensor stayed in place for the full term of the 3 weeks. And going kind of skipping that second question because you asked it in the third part, would leaving it in place have an influence on soil conditions in the chamber compared to field conditions? And most certainly. So it is not a clear chamber, so light can't get through, so that can affect the heating and cooling of the soil. If irrigation comes through, it might take a while for water to get actually under the chamber because it can't just fall directly on it. You kind of have to rely on matrix activity to move the soil for the water to get under the chamber and then absorb back up underneath. And then there's also the issue of if we are measuring carbon decomposition essentially, and we're decomposing all the carbon in this one area under the soil and kind of concentrating it right there, how is that going to affect what we're measuring? So the decomposition rate of organic matter might be completely different under the chamber just because the chamber isn't there. So that's one of the chamber effect things I was talking about earlier, where us measuring soil fluxes inherently changes how those fluxes happen from a biological standpoint, from a physical standpoint. It's just a challenge that's really hard to overcome. For a manual system like I have, it's really easy to move the where I measure from because it's just a PVC collar. I can pick it up, move it, and I try to do that a couple times a year. You can also do that with the agrology system, but you're kind of striking a balance of, and I'm not trying to speak on agrology's behalf, but this is just the experiences that I've had. Is yes, I could take the T-post out of the ground, move the chamber, put it back in, and from another spot. But what's the damage I'm doing from moving the chamber? Having other physical changes to the soil from reinstallation again, but how does that balance to keeping soil in one spot? So there's just a lot of different things to understand. It's hard to cover all of that in one study, but these are all things I think really need to be addressed by all kinds of soil gas flux research if we're going to try to use some of this data to affect things as important as climate policy, payments to farmers. We really need to make sure that we're doing all of this correctly. And I don't think we have the perfect system for that yet. So I think we have a long way to go to try to get the perfect system for all of this.
I would probably just chime into that one and say that as we start getting into this business, we're probably going to realize that we know less than what we thought that we actually knew. I think that with what we're seeing at full scale for our 6 sites, the spatial temporal heterogeneity that we're seeing is really putting up more questions than we have found answers. We directionally can confirm what we would want to assume, but yeah.
Yeah. All right. I think that's all the questions we have. Somebody has one more they want to throw in really quick. But I want to thank everyone again for coming. I really love discussing these topics because it's questions that I think about every day. And thank you for Agrology, of course, for having me. And Holly, if there's anything you need to close us out, I'll let you do that.
Thanks, Nick, and thanks for all your work on the slides and for sharing the information. Again, we'll follow up with an email in the next 24 hours, and it'll have the contact information for Adam and Nick if you have any further questions. And thank you, Dr. Michael, for being here and weighing in as well. And please reach out if you guys have any questions, and hopefully we'll see you at the next webinar.
Thank you, everyone.
Thanks, everyone.